And for the range, we will do exactly the same thing. I'm going to skip over the horizontal asymptote. So I'm going to go from negative infinity. I'm going to skip over 0 because it's this parent function. That's where it's sitting, all the way up to positive infinity. Now, what we require when you are actually graphing this, we don't make you do a ton of points for this. There are 2 points that we want to see on your graph on your test. And that is going to be this 1, 1 point and this -1, -1. Because that should be enough for you to know where and what section the curve is going to be. So the only thing you have to graph is that singular point. If you want to plug in more, you can, but that is going to be the point that we require. And I'm going to make a little note, required point. Just so you know, on your test, if you are graphing a parent function, we are going to graph these 2 things. Now, this point may move depending on if you have transformations, but that is the you know how we have points that we memorize for quadratics and square roots? That is the point, 1, 1 and -1, -1. So now we're going to kind of go in and look at transformations. Transformations work almost exactly the same as they do for anything else that we've done. On the very bottom of your page, you have something that kind of lays out the transformations for vertical stretch, vertical compression, moving left, right, moving up, down. They are identical to what we've been doing. This A is my vertical stretch. We really don't ask you for vertical compressions identification in these types of questions simply because it kind of drops into the denominator, which can be a little bit confusing. Anything here is going to be left, right, because anything with the H is horizontal, and you're always going to do the opposite of what it looks like because of that negative. And the K is going to be your up, down. And then, of course, if there's a negative on the front, we are going to reflect over the x-axis. All of these are what we've been doing. There will not be any horizontal stretches or compressions on questions that you will see in this class. So it will just be basically a vertical stretch when it comes to this parent function. We will eventually talk about different things and different ways to graph rationals, but for these types of problems, we're sticking to vertical stretch. So now, knowing what those transformations are, because we should hopefully know them from the many, many times we've done it this year, looking at example 1, I have 2 things, because remember, if you're trying to identify transformations, you're comparing it to the parent function. The parent function is 1 over x. So there's 2 things that I notice that have kind of moved from 1 over x. I have a -2 here, and I have a +3 here. And those are going to be transformations that I have to apply. What does the -2 mean? Right 2. And what does the +3 mean? Up 3. So all that we have to do, and what I do, is remember, in the parent function, those are horizontal and vertical lines at x = 0, y = 0. So I just move my vertical asymptote to the right 2. So I'm going to take it over 2 points and go through +2. It would be exactly kind of like how we've been graphing before. That puts my vertical asymptote at x = 2. And then the same thing for the horizontal. Normally it's at y = 0, but we're moving it up 3. So it's going to go up 1, 2, 3. And so that's going to put it at y = 3. And even without graphing anything, the same format that we did for the parent function works for domain and range. I'm going to skip over the vertical for the domain. I'm going to skip over the horizontal for the range. So I'm going to write that out really quick. Negative infinity all the way up until 2, because that's where the vertical is. to positive infinity, and then negative infinity, skipping over 3, union 3 to infinity. So where do I actually put my points? Remember, there's two things that you have to graph. Typically, we graph the 1, 1 and the negative 1, negative 1. So even though it's not a point that we write down on our paper, the intersection of your asymptotes, where they cross each other, that's like your 0, 0. So I'm going to put my first point, I'm going to go right 1 and I'm going to go up 1. So when I put my point down, it's going to go here. And then from that intersection again, I'm going to go left 1 and I'm going to go down 1. And these are the only 2 points that we require. Now, if you want to do more, you can do more. But having those points tells us enough to be able to, for the most part, get the idea of what the graph should look like. Because the shape itself should not change. The shape should be exactly the same. It should still be 2 curves, one in one corner and the other in the opposite corner for these types of graphs. Okay, do I have any questions so far? Yes, Site. The one that you have on your paper? Okay, what about it?
How did you graph the first part? I don't understand how I got that.
What do you mean?
Like, how did you graph it?
I took the points from the table and I put them on my paper.
Oh, wait.
They came from the table. We filled in the table.
Oh.
Okay, so the next type of problem that you could potentially encounter. Let's go to the back. When we have transformations, we have a starting graph and we have an ending graph. So what transformations, Gabe, are on f of x? Let's see.
On
F of x. For example 2.
Down 2.
Down 2. I like down 2.
And down 3. To the left 3.
Left 3. Now, this type of question is tricky for people because they just identify the transformations. They say this has this transformations, this has this transformations, and then they move on. But the question specifically wants to know, how do I get from f of x to g of x? So this is where I'm starting. I'm starting down to left 3. Where am I ending? With, well, hold on. What are my ending points for that g of x function? Right 2, okay. Right 2, up 4. Now, there is one transformation that's happening that we can kind of just identify that you don't have to really think too much about. We went from 1 to 2, so that's a vertical stretch of 2. But the difficult part is the movement. So when I go down 2, I'm actually at negative 2. When I go up 4, I'm at positive 4. So how do I go from negative 2 to positive 4?
Up 6.
Up 6.
Right 5.
So we went up 6. Now, when I'm going left 3, I'm at negative 3. And then when I go right 2, I'm at positive 2. So how do I get from negative 3 to positive 2?
Right 5.
Right 5. So when you get questions like this, because you may see questions like this again, make sure that you're very careful, because the common mistake that we see is people identify the transformations. They're like, well, it's this, but they don't actually talk about how do I get from one graph to the other. And the answer is this part where you're describing those transformations and how we get from one function to the other. It's not identify the transformations of both functions, it's just how do I get from one to the other? Okay, for example 3, we are going to go in and we are going to write out our transformations. The first thing that I'm noticing is there's a negative at the very front. And so anytime you have a negative at the very front, that is going to be a reflect over the x-axis. And if you have forgotten what that does, that is going to change the sign of the y values. So, other things that are happening. We have a -4, we have a +2, and that is basically going to move my graph. It's going to move it to the left 2, and it's going to move it down 4. The first thing I always do is I put the vertical and horizontal asymptote down on my paper. And remember, they're normally at x equals 0 and y equals 0. You're just moving them according to the transformation that you identified. So I'm going to go to the left 2. And I am going to go down 4. And that should give me my horizontal and my vertical asymptote. Now, the one thing that is going to change based on the reflection over the x-axis. Normally, we have the point 1, +1, -1, -1. But remember, it's going to change the sign of the y values. So instead of having +1, +1, we're going to have +1, -1. Yes?
Is there anything that would be reflection of the y-axis?
Not that we're going to give you. It would, if it were, it would be within the denominator, but because it's hard to identify when it's inside, outside, we just treat it as an x-axis. And then for the -1, it's going to have a +1. So that basically just means our points, instead of going upwards on the right, it's going to go downwards, and it's going to kind of flip. It's going to look like this. Let's do it in black. One thing to remember, because I don't want you to make the mistake of drawing your line in the wrong direction, you should never be crossing your dotted lines. Those are like your barriers. They're your boundaries. They're your gates. You cannot cross them. So don't think that it always has to go down on the left. It's going to follow where the points are. And so when I go in to write this domain, the domain itself actually doesn't change because you still have graph covering all of the pieces that you need it to cover. So we're going to go from -infinity all the way up until -2, all the way to +infinity. And the same thing for the range. It's going to cover everything except for -4. So the only, for these types of problems, I guess the only thing that you should really be careful of is how is it moving left, right? How is it moving up, down? Because that's going to fall into what's the vertical asymptote, what's the domain, what's the horizontal asymptote, what's the range. There are only 2 points that you have to plot. These are the only 2 that we will require for this type of question. Eventually, we'll get to some more complicated things, but this is the basic standard rational parent function with transformations. Okay, any questions before we do some factoring review? Because this is the new stuff. No? Okay. You should be able to do 1, 2, 3, 4 in like no time. Like this, snappy. I'm gonna go through these quickly. This has a equal to 1, so I can use the shortcut. What multiplies to -12 adds to 1?
3, -3, +4.
Almost. Oh wait, that's right. You said -3, +4?
Yeah.
-3, +4. I like -3, +4. If I multiply them, I get -12. If I add them, I get +1. With the shortcut, when a equals to 1, you can just say x minus 3, x plus 4. What do I do for number 2? GCF, thank you, Jaden. 4, x squared plus 2x plus 1. because it's not 0, it's 1. Now, the reason why taking out that GCF is really nice is because it gives you a question that is now an A equals to 1 problem, which is nice because you can use the shortcut. What multiplies to be 1 and adds to be 2? 1 and 1. So 4, x plus 1, x plus 1. You will have to be able to factor for these next couple of notes. Like, as fast as I'm going, you have to be able to do it quickly. Otherwise, it gets really, really complicated because this should not be the hard part.
We have no notes.
Huh?
We have no notes.
What do you mean?
No, we were never gonna do notes again for the rest of the year. Ever.
Okay.
I feel like after this. No.
You have like mini notes after
No, like,
this.
After like right now.
Right now, no.
Okay, yeah, it's my question.
We are doing notes right now.
Yeah,
We are in notes. I need something that multiplies to be 6, adds to be 5. 2 and 3. Now, can I use the shortcut on this problem? No, because A currently does not equal to 1. So if A does not equal to 1, you have to split the middle term. So that means I have to take 5x and I have to write it using the 2 and the 3. This is not brand new information. This is information that we have learned in this class. We group the first 2, we group the last 2. What is the GCF of my first group? Only 2? 2x. I'm left with x plus 1. What is my GCF of my second group? 3. I'm left with x plus 1. You get one factor from your parentheses because they should match. So one factor is x plus 1. You get your second factor from the GCFs that you used. We used 2x, we used 3. So my second factor is 2x plus 3. Okay. Last one is it's a special rule, but you can think of it as a regular factoring problem. We had something where there was a difference of squares. It was a plus b, a minus b, but you don't have to use that rule for this problem because you can still think of it as I need something that multiplies to be negative 36 and adds to be 0.
6 and 6.
Positives?
Oh, negative 6, positive 6.
Negative 6, positive 6. They multiply to be negative 36. They add to be 0. So they turn into x plus 6, x minus 6. Now, that is the same exact factoring from the rule. But if you know you're never going to remember that rule and you're not going to think about it, you can still treat this like a normal factoring problem. Yes, Jaden?
Where you get the 0 from?
Is there a b term? So there's 0x, which is why we fill in 0. Okay, any questions? Put in a pass. I need